If there is a bijection, then the cardinalities are equal, that are quite easy to see, right? And if the cardinalities are equal, that then we have a readily available bijection between them, right? So, we are going to work with this thing and extend it further, that the cardinality of two sets are equal if and only if there is a bijection between them, if there is a possibility, if there exists a bijection between them. Okay. So, then we talked about it and then we stopped here, that a set S is called a countable set if it has the same cardinality as the natural numbers. Okay. We just give it a name, some special set, we know when do we know if they have the same cardinalities, but if a set has equal cardinality as that of the natural number, then we call that set a countable number. Okay. So, if you rephrase it in this term in view of the previous slide or the last lecture summary, is this basically can be translated as this thing, that a set is countable if and only if there is a bijection between that set S and the natural number, right. So, this is just a translation or substitution of the word same cardinality. This, if there is a bijection between the set S and the natural number, then that set will be called countable set. Okay. Please understand this thing. Okay. Understand this this thing, the next two sentences that I am going to tell you, and it is going to, we are not going to talk too much about countability, we are going to talk about uncountability. Okay. So, what does it mean for a set to be countable? When you have a set which has a bijection from or with the natural numbers, what does it mean? It is a natural number. So, you can kind of impose some indexing on the set S, right, or some what is it called, order on to the set S, right. There is some kind of ordering. What is the first number of S, the first element of S? What would be the first element of S? S is an unordered set, right, unordered collection of objects. But now I know there is a bijection from between S and N. What could be called as the first element of S? Yes, the image of 1, right. 1 is a natural number, the image or the pre-image of 1 is a bijection, right. What will be the third element? The image of 3, right. The seventh element, right. So, this is this, you see, if we are counting, right, the first, the second, the third, right, if we can kind of count all of them, we can count all of the set S, that is why S is called countable. Okay. So, in the following set, suppose I can count or write or see or process or print one element of S per second, or per millisecond or per nanosecond, whatever, right. But if in a finite time I can do one element, then you can think of any element of the set after a finite amount of time I will be able to print it. Does this make sense? So, let us say in 1 second, think of a number in S, some S, an element of S. Well, there is a bijection from S n to S, right. So, let me now I can say, think of the 19 trillion 4 billion 7 million 70 million 5832th element of S. Will it be printed? When will it be printed if I run this algorithm?
That seems
No, say it, that is your ICP. So, which after how much time will it will be printed after 19 trillion and those many seconds, right. Is this clear? So, this is what it means for accountability. Can I print the whole set S? Can I say that the whole set S is printed? No, it is an infinite set. It will never finish, but anywhere you want to reach, you will reach in a finite time. This is the definition of infinity. Okay, this is what infinity means. That is why we generally say, well, the answer is infinite, it is an infinite number. There is nothing called an infinite numbers. All numbers are finite. Infinites are sets, right. It is a cardinality question. Sets have infinite cardinality. Okay, numbers are not infinite. Numbers are numbers. Okay, make sense? Okay. So, look at this. So, we can this is the bijection. Okay, so S has elements a1, a2, a is some elements a, but now I have a bijection. So this a1 is what you said f of 1, this is f of 2, this is f of 3. So I can write this, right? I can count them, I can iterate through them, I can just traverse through any, but with the property that I will reach any element you want me to reach after a finite amount of time. Okay, I will never be able to finish the whole set, writing the whole set, but after a finite amount of time I will reach any set. Okay, so this is the thing we saw last time also. Are these sets countable? Right, what is, by the way, a set is countable? We saw a set is countable. If it's finite, it's definitely countable. If it's infinite, then it's countable if it has the same cardinality as n, right? If they can be placed in a one-to-one correspondence with n. Okay, so is Z countable? The set of integer, does it have the same cardinality as n? No, it's not, doesn't have the same cardinality as n. Okay, we saw it last time. What if I make, so let me just give you this set, this function f from n to z, right, where f of I is equal to I if I is even, and f of I is equal to negative I if I is odd. Is this a bijection? It's a good, last time we saw it, the set of positive integers and the set of negative integers, the set of all integers, they have the same cardinalities. Okay, look at this, is this function a bijection? No, why not? It's not one to one. Which two have the same images? Give me two numbers who have the same images. F of 1 is what? And what with f of negative 1? No, f of negative 1 is not even a question, right? Negative 1 is not in the natural number. So give me two elements of n who have the same image. F of 0 is 0. So no, f of 1 is 1. 1 is odd number, right? So f of 1 is negative 1. F of 1 is negative 1. What is f of 10? What is f of 10 here? 10. What is f of 9? No, I'm doing something mess. Yeah, you're right. So I'm making mess. Yeah, yeah. It's not on to. It's not 1 to. So what should I do? Let me just write it like this. F of I is equal to. So what I want to do is, so even numbers I want to give to the positive numbers, right, and odd numbers I want to give to the negative number. The ith even number will go to I. The ith even number should go to I. Okay, let me just write I divided by 2 if I is even. Okay, and f of I is equal to negative I over 2 if I is odd. Ab khush ho? Yes, look at this now. What, let me just see, what is f of 2? What is f of 2? 1. What is f of 3? What is f of 3? Negative 1, right? What is f of 4? 2. What is f of 5? Negative 2. F of 6? 3, right? F of 7? Negative 3, right? So the function is onto. All positive negative number covered zeros, all positive negative numbers are covered. 1 over 2 is not there, na? Where is 1 over 2? It will never give you 1 over 2. If I is even, I over 2 is an integer. and if I is odd, then I minus 1 is an even number, right? So, even divided by 2 is an integer. Okay, so look at this. It's very similar to what I constructed is very similar to this. How many numbers seem to be n has all positive integers, right? E is all positive even integers. Seems like E has about half the content is there in n, right? But if you look at it like this, how many? So, if you look at it like this, it looks like E has fewer number, right? Fewer elements. But if you look at it like this, then you see that there is a first even number, then the first even number goes to the first natural number, the second even number goes to the second natural number, the third even number goes to the third natural number, right? And that is what gives us that there is actually exactly the same number of elements. Make sense? The function there was that this function, you can write this function and this gives you that this is a bijection, right? Not easy. I constructed this function. Look at this function. One can write very easily in terms of 2i minus 1 something, but this function is a bijection. Yes. If you can prove that there does not exist such a bijective function, then they are not the same cardinality, or you can say that the function is the set is not countable. So, there are ways to prove it. So, we proved in many cases yesterday we said, so if 10 people go to a hotel where there are only 9 rooms, can there be a bijection? Yes. So, that kind of reasoning you do, and you just find out disproving something is, so we will see, by the way, there is not at least one side of it is what we will do when we do counting pigeonhole principle. So, the set Z is countable. Okay, the set Z is countable. Again, if I just use this bijection, when will I print negative 17,832? When will I print negative 17,832? Sorry? That because the definition of the cardinality. This is the statement is stated. The question is phrased like this: how is Z countable? Z is countable because it has the same cardinality as n. Can you guys please stop talking? Stop talking, please. Yes. No, it doesn't. Well, I just showed you the thing. We talked about it last time also a lot in very into quite detail, that these infinite sets behave really differently. This is what you look at it. That let me just show you exactly that example. N and S. This was that example. If you look at it, like see, 3 is there in left side and it's not there on the right side. 7 is there in the left side, not there on the right side, right? So, S has fewer elements. But if you look at it, for any number there is a square. For any natural number there is a square, corresponding square, that is that 1-to-1 correspondence. Any number has a counterpart here, or because it is a bijection, any integer here, any positive number has a unique counterpart here, and that is the way we count, right? Things are equal when you can have this correspondence thing there. Okay. So, long ago, yes.
So my question is that we just proved that the cardinality of integers is equal to the cardinality of natural numbers.
Yeah.
And then here we're proving that the cardinality of the set of squares is also equal to the cardinality of natural numbers. But we know squares are a subset of integers,
Yeah.
so how can their cardinality be?
Yes, that's because that's the definition of cardinality. This is what last time you kept on nodding heads. Look at this is what it is. Infinite sets behave differently. It is counterintuitive. Cantor said, I see it, but I don't believe it. It's counterintuitive, right? We think, okay, the positive numbers have only half as many numbers as all the integers. Positive integers are it's exactly half as, but this statement says, okay, essentially this says this is not technically correct thing, right? This is not technical. So, this is what the statement is: half the cardinality of half is bigger set is all integers is actually equal to in the same cardinality. Okay. So, it is such a deep thing, that is why I asked you that pay attention to this in detail. Okay. The set O, and this is only even numbers, or let us say O we defined it to be even odd positive integers and E to be even positive integers only. They have the same cardinality as n, right, because we can count. So, they have these are countable, because there is the first odd numbers, the second odd number, the 19th odd number, the 85th billionth odd number. There is this one-to-one correspondence between O, E and n, right, each one of O and E with n. Similarly, integer powers of 2, we saw it earlier. There is the 19th power of 2, then there is the 18th power of 2, there is the 17th power of 2, and there is a one-to-one correspondence. You can find a one-to-one correspondence. And all of them we saw, these are all countable sets, okay, countable sets. So, think about it, just please pay attention to this thing, because I am going to build up two more very deep results. First is, we talked about cardinality of finite sets, then we extended and talked about cardinality of infinite sets, right, and then we found a special category of infinite sets that are countably infinite. Right. So, the question, and all of these sets that we have been working, they are infinite, they are all countable, right. Any others you can think of many more from the previous slides. So, the question arises, is that it? Is all infinite set actually countable infinite, right, or is there something that is even bigger than n? That is the question. That was the question of that bothered mathematician for a long time, okay, and was resolved like a century ago by George Cantor, that no, that is not true. Not all infinite sets have the same cardinality, essentially saying there is not one infinity, there are multiple levels of infinities. Okay, this is a continuum hypothesis, that is what is actually the continuum hypothesis, that there are these levels of infinity. Then assuming conjectured is that there is actually an infinite levels of infinities, right. We are going to study two, the Aleph null and Aleph 2, Aleph null and Aleph 1. Okay. So, we showed that powers of 2, squares of 2s, squares and cubes and all these integers are actually, all these sets are countable infinite. So, are all sets countable infinites, right. More precisely, I am going to ask, is the set of positive rational numbers, right. So, positive because it is easier to draw and write, is the set of positive rational numbers countable or not? Is the set of rational numbers infinite? How would you convince me the set of rational numbers is infinite? Yeah. So, it's the natural numbers are is a subset of the positive rational numbers, and the rational numbers is, natural numbers are infinite. So, there will be infinitely many rational numbers, right. There are many more. So, let us see if this thing, we should be very, very careful. Rational numbers are very, very dense. Okay, it is a very easy theorem to see that between any two rational numbers there is another rational number. Can we say this about integers? No. Can we say this about squares, about cubes, about powers of 2s? Is there any power of 2 between 16 and 32? Right? Is there any integer between 5 and 6? So, we can't say this thing, and that is a very density statement, that just way too many, just give me any two, there is no range or no interval is short enough, right. I can find even shorter interval, right. And namely, how do you get a rational number A, get a rational number B, take their arithmetic mean, take their average, A plus B divided by 2, that is another rational number. If A and B are rational, then A plus B is rational, right. We saw that. So, it is another rational number, and that rational number is now even shorter interval, right. So, this is a rational number between A and B. We also saw this thing earlier, that the min of x plus y, min of x is less than or equal to the sum, and max of x and y is bigger than or equal to the sum, right. So, this a plus b divided by 2, the average is actually, no sorry, max is greater than or equal to twice the sum, twice the average. Okay. So, let us see, I am going to argue that actually there are only countably infinite many rational numbers, positive rational numbers, right. So, I am going to arrange a positive rational numbers in a 2D table, okay, like this, okay, in a matrix, or what do you call it, 2-dimensional table. Is any positive rational number missing from this table?
Yes.
Which one?
3 by 2.
3 by 2 is missing. So, 3 by 2 will be there in the third level, it is right here. Okay. So, understand this thing, how are these rational numbers written? All rational numbers whose denominator is 1 in the first row, all rational numbers whose denominator is 2 in the second row, and so on. Okay. So, is any positive rational number missing from this table, right? So, now I am going to prove to you that this table or this set is actually countable. Countable meaning what? What am I going to do? I need to tell you that this is exactly the same cardinality as n. I need to give you a bijection. So, I am not going to formally give you a bijection, you will do it in your homework. I am just going to argue the informal definition, that what in essence this definition of having a bijection with n means. Having a bijection with n means that you can start writing, and then there will be the first number, the second number, the third number, and all numbers will be right. So, start writing, and you have to argue that every element will some point will be printed, right. So, if I start writing like this, if I write list, count, print these numbers like this. So, let us the first row is called the row major counting of matrices in 2D arrays, row major thing, we saw this in summation. What will happen if I start counting like, does this prove that this is countable? The set is countable, but this does not prove it, right. Why? When will be 3 over 2 printed? When will 3 divided by 2 be printed? Can we say that after finite amount of time any number will be printed or listed or written? No, right, because f of nothing under this bijection, this function, f of nothing is equal to 3 over 2. There is no integer, there is no positive integer such that f of x is equal to 3 over 2, right. The system says f of 1 is 1, f of 2 is 2, f of 3 is 3, f of 4 is 4. It will never reach f of 3 over 2, right. So, let us do it column measure. If I print them like, start printing like this, when will be 3 over 2 printed? Or 2 over 3, when will be 2 over 3 printed? Many will be missing, right. So, this function, this function is f of I is equal to 1 over I, right. F of I is equal to 1 over I, and just will never finish, right. But if I start counting or start listing them like this, now when will p over q be printed? Can somebody say that this the pth row and qth column elements is missing? When will it be printed? How big will that point be? Is a function of p and q. When will you reach I over j row? Okay, it is not very difficult to see this thing. I am just asking after how many seconds I over j will be printed if per second you do one printing. Okay. So, here is a matrix, this is the matrix here. When I reach this some number I over j, and I am printing things like this, right. So, I would have printed all of this stuff. How many elements are here? This is I times j, right. This matrix is I times j. This is a triangular matrix, right. This is essentially ij divided by 2, and this upper triangle thing is also ij divided by 2. So, in 2 times ij after 2 times ij steps. So, if you say when will be 17 million divided by 4000 printed, I will say just wait for 17 million multiplied by 4000 times 2 seconds, and this will be printed. Any number you can think of will be printed after a finite amount of time. Okay? Or this is exactly what actually what you can say, that what is, if somebody asks you f of what is equal to 17 million divided by 4k, that's roughly speaking, I don't know, just do the calculation, f of x, so x is equal to 17 million times 4k times 2, okay, roughly equal to this thing. So, I gave you a bijection. This is the bijection, this is the way I described it differently, but you can just write the formula, right. Those of you who have done C++ code and stuff. I can repeat what again? That's a good thing. That's so look at this. When I am printing this, what must have I printed? When I reach this, what must have been printed? Everything on the top left portion, right. This matrix will be totally printed. This is the 5th row and the 4th column, or the vice versa, 4th column and 4th row and 5th column, right. So, that is a 4 times 5. I must have taken 4 times 5 steps to do this, to print this, and then I must have done something like this, right. These will be printed. Look at this. So, when I am printing 3/2, I have not only printed the upper submatrix, I have also printed some of these triangles. The print, this is called a dovetailing thing. It's no big deal. Don't get confused in this thing. Okay, absolutely nothing. Just what you root. This I just didn't give it couldn't give it a name. Counting them in this dovetailing fashion. So just this picture. This picture tells me that everything will be counted after a finite amount of time. If you really want to find the precisely what is that time, you can do this. The reason I won't go into the details of this right now, because if you see this table, there is a lot of repetition. Is there a repetition? Right? So, one is repeated, one is repeated. Many things are repeated. So, all the diagonals are actually equal to 1, right? But there are other stuff that is repeated, right? So, 4 over 3, then there will be 8 over 6, then there will be 12 over 9, right. All of them are just repeated. Every number is repeated many times. So, if I start to give you this thing by this picture, that is why I said this roughly equal to, then actually this q plus, the way it is shown here, is not even a set. Okay. So, you have to be careful and do this, not do the over counting and stuff, but convince yourself that there is, if I start, that is why it is important to understand this informal definition of countability. They start counting. Can you count anything you want in a finite amount of time? Any number, any element of the set in a finite amount of time. Okay. So, this kind of gives us this idea that okay, all the sets we have seen, all the infinite sets we have seen are actually countable. They have the same cardinality as n, so they have the same cardinality. Is it true that all infinite sets have just are countable, or they all have the same cardinality? So, this is the greatest one of this is called the Cantor's great theorem, Cantor's second great theorem, which says that no, actually not all infinities are of the same thing, not all infinite sets have the same cardinality, right. The method is even more important. Those of you who study theory of computation or even algorithm, you will see that diagonalization is one of the very important, very powerful tool to in computation and theory of computation and all of mathematics. Okay. So, we will study diagonalization, and I will prove to you that the set I of all real numbers between 0 and 1, this is not countable. It has strictly more cardinality than the set of natural numbers, right. There is no way you can start writing in any fashion, you can write the real numbers between 0 and 1 only, so that every number will be printed after a finite amount of time. Okay. You cannot just write them, you cannot count them. Yes, please. What is infinity? No, sorry. There are infinitely many numbers between 0 and 1, yes. Yes, it will be even more.
So then by this logic, some infinities are larger than others?
No, that's a very good point, but no, that's not what I am saying. I am saying the number of real numbers between 0 and 1 strictly more than the number of integers or the number of rationals. I did not say that the number of real numbers between 0 and 2 is actually double that. We will actually, this is not very difficult to see that the number of real numbers, the number of real numbers between 0 and 2 is just double than the number of real numbers between 0 and 1, which is the same as the number of these two, twice that second infinity is the same as the second infinity. Okay? Yes, please.
But we can't write down all natural numbers either.
You cannot write down all natural numbers, we never claimed. We claimed that if you start writing them, you will reach any natural number. That was explicitly my statement, that we are not saying, you see, this was explicitly we said, we are not saying that the whole set will be printed. All natural numbers will not be printed. It will never be printed. But you can think of any number that will be printed or at some point or counted at some point. Okay, see, arguing about infinity is way too much. There is a whole beautiful book called Limits of Mathematics and Mathematics of Limits. It talks about this stuff, right? The mathematics of limits and limits of mathematics. These are deep concepts, so it will take some time for you to digest. Yes.
The set of irrational numbers between 0 and 1.
Sorry, say it again.
Is the set of irrational numbers between 0 and 1 finite or infinite?
The set of irrational number.
Between 0 and 1.
Well, that's a really good question, a very good question. The answer is it's infinite, of course, infinite, the set of irrational number. Actually, it's much more, it's the larger infinity. Okay?
We say that is as irrational numbers and rational numbers are essentially real numbers, so that's why it has a bigger infinity.
Yeah, so that's what. So this is 0 and 1. This is how we write the interval, right? Let me just draw it like this. Some numbers here in this open or closed interval, some numbers are rational. We saw they are countably infinite only. The remaining numbers are irrational. They must be infinite too. Those are the people. There are actually many more than these rational numbers, which actually doesn't make it. It's that infinity is twice the. So there is this. What did I give? So again, nothing is here is not correct. Okay, do not quote me for this. If the rational numbers were kind of infinite, if the irrational number were like roughly the same as q plus, then roughly speaking, we are saying all the numbers here are just twice this infinity, and that will be still countable, right? So this irrational numbers are actually adding much more. It's much more. Okay, so again, the statement is deep. It's important, right? But the technique is much more important for you. Okay, for your careers or your understanding of things. Okay, so the diagonalization technique. We are going to use a proof by contradiction technique. We are going to prove that if the numbers between 0 and 1 I, the set I was countable, then something really bad happens. Okay, that's what we are going to do. So for the sake of contradiction, assume it is countable and substitute the definition of countability. If the set I is countable, that means there is a bijective function between n and that countable set. Okay, there is a bijection, there is a bijective function between the n, the natural numbers, and the set I. Countability means we can count them, we can list them, we can start printing them, right? So let's, for this, because we have assumed that there is countable, so let's start counting, let's start writing them. Where is the first number? What is f of 1? What is f of 2? What is f of 3? So start listing them, right? These are all real numbers. 0, the set 0, the set of the interval 0 1, right? The set I. All numbers are 0.1, 2, 7, 9, 1, 2, 4, 8, whatever, some 0 point something, right? So I'm going to look at those list numbers in this order. What is the order? That is the bijection between n and the set I. Whatever is f of 1, I will write it as the first number. Whatever it is f of 2, I will write it as second number. F of 3, I will write it as the third in the list. Is this clear? Is this clear? I assume for the sake of contradiction that the set I is countable. I substituted the definition of countability, that there is an ordering can be imposed. There is a bijection between n and I. I am just giving the list representation of that bijection, right? The list representation of that bijection. So, the numbers are going to be like this. This is the, what is this thing? This is the fourth digit of the fourth number. This is the first digit of the third number. This will be the 19th digit of the fifth number, and so on. Okay, some numbers, these are some numbers, 0 point, all of these are between 1 and 9, right, between 0 and 9 inclusive. Okay. Now, I am going to just write it at the table, so that we are going to, so in a row column format. List is a different thing. Is this arrangement clear? What is the first number? What is the first, which one number is R1? Not the value of it, but why did I write R1 in the first number? Because it is mapped to 1, or 1 is mapped to this thing, it is assigned to 1. Okay? Because it is a bijection, so assigned and map is the same thing. So, what is R2? It is the number that is assigned to the number 2. What is R7? That is the number that is assigned to the number 7 by the bijection. And 0 point is common to all of them, so I just ignore it, right. So, picture the bijection like this, the list representation of that supposed bijection, right. And furthermore, just focus on the diagonal of this, focus on just the ith digit of the ith number, that is the diagonal, ith digit of the ith number. Okay. So, this is what we are going to do, and looking at this I am going to construct a number. Okay, I am going to construct a number. I will look at this list L, and this number I will call it SL. I will make sure the number is between 0 and 1. So, it belongs to the set I, and that number will be 0 point some digit, then some other digit, then some other digit C2, then some digit C3, then some digit C4 and C5. Is this clear? So, these are just writing, I am making a number, I am constructing a number, or I am writing a number. Okay. The way I construct this number, the way I challenge, make this very challenging number is as follow. Okay, very simple rule. I look at these green numbers on the diagonal. Okay, if the first digit of the first number, if D11 is 7, I make C1 not 7, I make it 8. And if D11 is not 7, then I make it 7. Why I do it, it will be clear in a minute, but is this construction clear? Okay, yes. It's written there, no? So why, what do I have to? I am saying I am going to construct a number SL, okay, that is the name of the number SL. This number is between 0 and 1, so it is going to be 0 point something 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 something, right. I am going to see what is that, those digits of SL, what is C1, what is C2, what is C3, right. So, I write CI is either 8 or 7, there are two possibilities, each digit is either 8 or 7. When is it 8? When is CI equal to 8? When the ith digit of RI is equal to 7, then CI is equal to 8, and when the ith digit of RI is something other than 7, then it is equal to 7. Okay. Now, the reason I constructed it, again I am going to give you a more concrete example, and so okay, so this table is going to expand. Now, look at this, I am asking, can this number that I constructed SL, can it be equal to R1? Can SL be equal to R1? Yes or no, why not? The answer is there. I am claiming SL cannot be equal to R1, because look at the first digit of SL, the first digit of SL is C1, the first digit of R1 is D11, and I made sure if D11 is 7, D11 is either 7 or not 7. If it is 7, then C1 is 8, and if D11 is not 7, then C1 is equal to 7, right. So, it was just by design, it was made to differ. C1 SL is made to differ with R1 in the first digit, maybe in many other digits, but the first digit is surely unequal. Yes. Yes, it's a number. No, it's a concrete example. You can make it different with some other thing, but yes, it is a concrete example. So, SL cannot be equal to R1. Why? Because D11 is not equal to C1. The first digit of SL is not the same as the first digit of R1. Okay. Can SL be equal to R2? Cannot be equal to R2, because the second digit of SL is not equal to the second digit of R2 by construction. Again, the second digit of R2 will be either 7 or not 7. If it is not 7, then C2 is 7. If D22 is 7, then C2 is 8. It's different than that, right? It was purposefully designed to be differ from every number. Can CSL be equal to R3? It cannot be equal to R3. The third digit will differ. Maybe other digits will also differ. At least the third digit is different between SL and R3. Can it be equal to R4? Cannot be equal to R4, because by design, you see, look at the substitute I equals 4 here. C4 is equal to 8 if D44 is equal to 7, and C4 is equal to 7 if D44 is not equal to 7. So, D44 is either equal to 7 or not equal to 7. In both cases, C4 is designed to be different, to be unequal. If this is 7, that becomes not 7. If this is not 7, then that becomes 7. So, they are different. Okay. So, this number cannot, new number I constructed, SL, cannot be equal to R4. Similarly, it cannot be equal to R5. Can it be equal to R17? Why not? Why cannot SL be equal to R17? Yeah, so what did I do in my construction? क्या 7 हुआ? No, I said 17. Na? Can somebody say that this SL is equal to R17? Why not? Sorry? So, the 17th digit of R17 is not equal to the 17th digit of SL. C17 is not equal to D1717, okay, and this is true for any I, right. If somebody says that this SL is equal to some Ri, I will say no, check the ith digit of that Ri and check the ith digit of this my number SL. They are not equal, so the numbers cannot be equal. Does this make sense? What does it give us? This gives us that the list L is incomplete. The list L is missing this SL. Now, let us just say the same thing as somebody says this number is already there in the list. So, where is it in the list? In the ith row? Well, I just said it cannot be equal to the number at the ith row. Does this make sense? This number is different than Ri, means this number is not there in any row. Cannot be in the ith row, cannot be in the I plus first row, cannot be in the I plus 17th row. Okay? So, the list is incomplete. This list is incomplete in the sense that this function is not a bijection. There is no x such that f of x is equal to this SL. So, this is not a bijection between these natural numbers and the number, all the numbers between 0 and 1. This number is clearly between 0 and 1, right. I wrote it as 0 plus point some digits, right. This is a number between 0 and 1, and you can show me that this is mapped or assigned. It is not assigned to anything. Okay. Now, so anybody who claims that, oh, I think the real numbers are countable, I will say, okay, give me the bijection, start writing them. So, don't write them all, but give me the code or give me a method, how would you write them. So, they will give me some method, which is this method that I pictured as a list, and I will say, okay, here is the number SL, you never printed it. you will never be able to print it, because that number I constructed after looking at your code. Okay. So, here is a concrete example. Yes.
So, but how do we say that we are disproving it by the fact that that number is not in that bijection, but maybe our bijection is wrong?
So, it is not a bijection, no. It is not. So, I say suppose this is countable, that means there exists a bijection. Then I say, hey, it is not a bijection.
Then we just looked at the diagonalization example and we did that if we go row, major, column, major,
That is not diagonalization, this is diagonalization. That is
the number won't be printed if we go in that way,
Yeah.
that way, but it would be printed if we go that way.
Yeah, so-
That means we can construct a wrong.
no, this is we did not construct it. You see, I did not construct this bijection. I said, okay, give me the bijection. It's a bijection means every natural number will be mapped to some real numbers between 0 and 1. So, I just looked at your bijection, any claimed bijection, and I constructed this real number. Okay. Any claimed bijection is actually not a bijection. That means bijection cannot exist. Yes. नहीं, हमने नंबर कंस्ट्रक्ट किया है, बाइजेक्शन को अस्यूम किया, सपोज देयर एग्जिस्ट अ बाइजेक्शन. That is the number we constructed.
How could we prove using this as a, this is not a general proof, right? Or
No, it is absolutely general proof. You are right. Yeah, please stop talking. We did not construct the function. We said, okay, suppose you claim there is a function, there is a function, give me the function.
isn't it just only one example and it was the
Which one is one example?
because this is like it was 7, 8 per
This is a different thing. No? The claim is here. The claim, this is the claim. This is the claim that there exists a bijection. So, you give me a bijection. Now, I am looking at, you claim you know the answer. Okay? And I am saying, give me the answer. And I found a mistake in your answer. That what does it mean? Any answer you give me. I am not saying that, okay, you write this is a journal thing. See, I did not write what is mapped to 5 or what is mapped to 7 or what is mapped to 19. I did not say that. It is a number between 0 and 1, right? Give me any answer, I will find a mistake in your answer. That proves that answer does not exist, right? Or you do not know the answer at least, right? Okay. Okay. Again, you need to think about it. You need to take a good cup of cold water, drink it, right? Spend 30, it may take a little bit more than 30 seconds, maybe a minute and 30 seconds, and understand it. Individually understand this, okay? And then you can talk about it. First, make up a story. All the stuff that I kept on saying, and then so talk about it, understand this. It's a deep question, okay? It's a deep proof. Okay? At least just fill in the English write up in your own words. What is the claimed, okay? It's complete thing. It's not there is no mistake here, but still you need to fill in some more details of it, right, to answer your question. So, here is suppose somebody claim here is my bijection, right, and I made this number CSL. This number is not going to be you cannot see this number in the list. This number will not be there in the list ever. Okay. Why? So, suppose somebody say, yeah, this is in the list. So, I say, where is it? It is in the 17,000 index, the 17,000 row. The f of 17,000 is this number. And look at the 17,000 digit of that number written in the list, and the 17,000 number of this number, this number, the 17,000 digit of this number. They are going to be different. So, now this is not written on the 17,000 index. It is not written on the any index. Okay. So, this is not cannot be a bijection, right. So, in summary, we defined countable sets, we proved that the set I of between 0 and 1 is not countable, right. That gives me, and this is infinite set, it is an infinite set, but even more than this, no matter how bijection you do, there will be some more elements, some missing elements, right, and those missing elements actually make it a bigger infinity, right. This is called the LF1, the second level of infinity, and maybe there are even more infinities than this, right? Maybe, we don't know. Okay, what we know about that? So, we solved one level of infinity, that is a countable infinity. Then we found this another level of infinity, the uncountable infinity, right? Can there be another level of infinity, that is some super uncountable infinite, right? So, this is the continuum hypothesis. The continuum hypothesis states the following: if you assume that there is an infinite hierarchy of infinities, or you suppose there is only these two infinities, the mathematics is going to remain consistent. Okay, so again, one of the most beautiful thing, the most powerful tool of that one is like the theoretical mathematics. This is for applied mathematics, right? That you are going to use this is the principle of mathematical induction. Okay, it's a proof method. It's a method. It's a way of thinking. It's a way of life. It's a really important thing. Okay, so is a proof method. We saw what is a proof. It's a convincing argument that establishes the truth of some proposition. Okay, and it's also has many applications in this stuff. We use induction to prove statements about all integers, or what's up infinitely many integers, right? All positive integers, or all squares, or all negative integers, or something like this, right? Induction is generally used for statements like these. Okay, so for example, this is a statement about all integers, right? Any n, for any n, add the first n positive integer, you will get n into n plus 1 over 2. Right? We saw 5,000 different proofs of this, right? With words, without words, and everything. You take any set who is cardinality n, for any number n, the number of subsets is equal to 2 to the n. This is a statement about all n, right? A statement about all integers, right? All cardinal numbers from 0 to infinity. These type of statements are proved using induction. Okay. So, now please pay attention to this thing, the principle of induction. Okay. Everybody should have seen this thing. If not, then please pay attention to this very simple induction axiom principle that we are going to establish. Suppose I have an infinite number of dominoes, right, arranged like this, the way they are. This is the best I could draw. Quite good, but the next are not as good as possible, as good as some. Okay, suppose I have an infinitely many numbered dominoes, right? I just put the number between them, and suppose I establish two facts, two rules, two given things, that two self-evident truths are provided. The first one is that the first domino falls. Whichever is the first domino, it will fall. Right, or it does fall. Okay. And the second rule is that whenever the ith domino falls, the I plus first will fall. Right. So, this is like infinitely many statement. This is a statement about all i's. Right. If the fifth falls, then the sixth will also fall. If the 19th fall, then the 20th will always fall. Also fall. If the 74th fall, then the 75th will also fall. Does it make sense? So, I have an infinitely many numbered dominoes. I have established, or I am given two rules, two facts about the world, that the first domino falls, and then the second, whenever the first fall, then the second fall, when the fifth fall, then the sixth fall, if the 19th fall, then the 20th fall, and this for all I, if the ith domino falls, then the I plus first domino also falls. Okay. So, suppose we live in this world, and let's apply these rules or these facts, right. Let's just put them into practice. I have infinitely many rules, and I apply those things. What does the fact 1 say? What does fact 1 say here? What is rule 1? If I apply rule 1, what will happen? The first domino will fall, right. If I apply rule 2 now, what will happen? The second will also fall, because rule 1 says for any I, rule 2 says for any I, if the ith domino falls, then the I plus first domino also falls. Okay? If the ith falls, then the I plus first will fall. So, 1 fell, 1 plus 1 will also fall, right? Domino numbered 1 plus 1 will also fall. That means 2 will fall. again rule 2, what will say rule 2 dictate? Rule 2 will dictate, because if the rule 2 says if the second falls, then the third should also fall, right. So, now by rule 2 the third domino will also fall. Then by rule 2 again what will happen? The fourth will fall. By rule 2 again what will happen? The fifth will fall. Can we conclude that all dominoes fall? Can just do it by democracy. How many of you think that all we can conclude, we can safely conclude that in the world where these two facts are simultaneously true, or these two rules are applicable, all dominoes will fall? Please raise your hand if you think all dominoes will fall. Please raise your hand if you think not all dominoes will fall. Anyone who thinks not all dominoes will fall? You think they will not fall? Good. You think? Okay, good. Anyone else? Okay. So, first of all, the yes wins by democracy. Even I had the RTS in my hand, so I could have decided anyway, but still you gave me a good majority. Okay. Why do you why do you think that maybe not all domino will fall, or which one will not fall, or what is the thing? So, I will come to the three of you who have.
So, if we take rule 2, assume for this to be true that all dominoes will fall, we need to have a last domino, right? But like there needs to be a last domino, but there is no last domino because there is always going to be an I plus 1 domino. Therefore, there is always going to be a falling domino.
Okay. So, okay, yes. Why do you think it's not?
Infinite number of dominoes और हमारा
Stop. हमारा क्या जा रहा है?
We are saying that हमारा if I falls then I plus 1 will fall, but the sequence is ongoing infinitely, then we cannot conclusively say कि एक time I
Very good. Very good. What? Who else? Yes. What? आपका क्या इतराज़ है? हाँ? Very good. Anyone else? Somebody was raising hand or trying to raise somebody else's hands. Remember that, right? Somebody, who was this? Somebody was trying somebody else raise hand. Any other question? Any objection? I have won the argument already, but still I can try to convince you. No? Okay. So, those two, let me answer that. It's slightly easier, actually roughly the same answer, same resolution. There is no temporal aspect to this. There is no time, there is no computation, right? Remember I said both the rules are simultaneously true. It is not a process. That okay, if one falls, then after 0.0001 second, I plus first will also fall, right? These are simultaneous rules. These are state of the affairs, state of the world. It's not a process. Okay, so maybe I wanted to use the word rule because this is given as a if then rule, but I also said the word facts. The fact is, if I falls, I plus first must also fall. Doesn't mean that I plus first will follow in falling after follow I in falling, right? It's not that first I will fall, then I plus first will fall. That if in this world I is falling, or I is fallen, or I will fall, then I plus 1 will also fall, right? Did it answer your question? There is no temporal aspect to this. Okay, it's not a process thing. Now I can see why do you get the thing why do you have this concern and stuff, but nobody defines or serve induction like this. I have a style of things that things are generally made much more complicated than they ought to be, right? If you look at this, so we saw we got a lot of votes for yes thing and everybody is convinced this thing. Now your question is roughly the same as what they said. There is no end to it. There is no end to what? There is no process. I didn't tell you a process, right? When I established, and that is actually amounts to the statement I said, the whole set will be counted, is a slightly different statement than saying any element of the set will be written or counted, right? Every element, every state So let's say you say if you think not all dominoes falls, right, then there must be a domino which didn't fall, right? Which one is that? Some number I, right? Some number I. That means I minus 1 fell, right? So if I minus 1 fell, rule 2 said I should also fall, right? This is what I use. It's called principle of well ordering, which we'll talk tomorrow, and we mentioned it previously when we did partial order, right? So okay, now everybody else is convinced, right? Those, are you still convinced or no? You still not clear? Okay, how about you? You're convinced? Okay, इनको पकड़ के बार समझा देना, समझा देना, okay? Okay, so now it's between you and them, okay, not me, okay? So here is the thing, hopefully it will be cleared in the next thing. This is where we are going to do proofs, right? We are doing mathematics. A proposition about all non-negative integers or many non-negative integers. Look at this proposition for all n p of n. This is actually not one statement, right? This is statement, this saying for all n p of n is true. It's actually a sequence of propositions, right? That's a quantified predicate. A quantified predicate is actually a sequence of proposition. It says p of 0 is true, and p of 1 is true, and p of 2 is true, and p of 4 is true, okay? Now hopefully the process perspective, the temporal perspective will go out now, because suppose I want to say all of these propositions are true. This is basically saying this can be thought of as given these infinitely many dominoes, and now my goal is to establish two facts, to establish the truths of two statements, one a fixed statement and one many implications, right? If I prove that p of 0 is true, if I prove that p of 0 is true, or in other words I say the first statement is true, right? The first statement that corresponds to in the analogy the 0th domino fall, okay, the 0th domino fall, okay, and then I prove to you for any k, if pk is true, then pk plus 1 is true, okay, for any k, if pk is true, then pk plus 1 is true. Suppose I establish, just convince you of these two statements, then can I conclude that p of I is true, p of k is true for all k, right? But then I can safely conclude by majority that p of n is true for all n, all dominoes fall, okay? Now you see, a statement, a proposition is either true or false. It doesn't become true depending on whether pi is true or pi is false, right? It's either true or false. That's what I said, there is no process of becoming true, or the falling is a process. Being true is a state, right? It's either yes or no, it's either true or false. Is this clear? Okay, so if I prove to you these two things, I can safely conclude that p of k is true for all k. Okay, p of I is true for all k. Just please keep in mind one thing. Does this prove that p of k is true? Does this prove that p of k plus 1 is true? Does this prove that p of k plus 1 is true? It doesn't. What if p of k is false and p of k plus 1 is false? What is p of k implies p of k plus 1? False implies false is still true. It doesn't prove anything whether p of k is true or p of k plus 1 is true. It just proves that these infinitely many implications are true. Implication is true. It only proves this thing. It only proves this thing, that it cannot happen that p of k is true for some k, for any k. It cannot happen that p of k is true and p of k plus 1 is false, because it says this implication is true. That means look at the truth table of the implication. It says if p of k is false, if p of k is true, then p of k plus 1 better be true. There is no option for p of k plus 1 in that setting. When p of k is true, the p of k plus 1 then cannot be false. That is the only thing it proves, the only possibility it excludes. Okay? Otherwise, it does not say it. P of k could be false, p of k plus 1 be true, that is okay, it does not violate this. P of k plus 1 and p of k both true is also a possibility. P of k and p of k plus 1 both true, both false is also a possibility. The only impossible statement, if this implication is true, if these implications are true, then for any k, it cannot happen that p of k is true and p of k plus 1 is not true. Okay? Just like in rule 2, didn't tell us whether the ith domino fall or doesn't fall, whether the I plus first falls or doesn't fall. It didn't fall. It just said that if the ith falls, then the I plus first will also fall. Okay, that's what it says. That doesn't say about each one. Together with p of 0, the first domino falling, together if you apply those in conjunction, then you can conclude that all dominoes fall. Okay, make sense? Okay, so let us do this. So, this is now the final statement of the principle of mathematical induction. Okay, you must have seen this thing called inductive reasoning. What is induction? What is how is math? One way to see it is how mathematics is different than other stupid stuff or even natural sciences. Is this deduction and induction. There we observe and we make a deduction, right? So, deduction, induction, reduction, these three words, you will hear reduction here a lot and induction a lot, not many deducing things. Okay? We do not observe things. Mathematics is not about observing and okay, good. Induction is not a process, that is a good thing. Induction is a statement. Okay, it is a principle, it is a statement, it is a claim or whatever, right. It is not happening, it is not a process. Okay. This is induction. Induction is a grand implication statement. If something, then if P, then Q. Okay. So, induction says the following: if P of 0 is true, and for all k, p of k implies p of k plus 1 is true, for all k greater than or equal to 0, p of k implies p of k plus 1 is true. Then these two, the conjunction of these two statements, actually how many statements are here? 3. How many statements are here? There are infinitely many, right? There is one of this thing, p of 0 is true, that is one statement, and then there are infinitely many implication statements, right. So, induction says together these two or these infinitely many statements implies that for all k, p of k is true. Is it clear? So, induction is a statement, it is written here, and in our analogy, the process, that the way we will do it is given here. If I want to prove that p of 0 is true and p of 1 is true and p of 2 is true, for all k, p of k is true, for all n, p of n is true, I can prove that p of 0 is true, and for all I, p of I implies p of I plus 1 is true, and that would, in our analogy, it will correspond to establishing the fact that the first domino falls, and the fact that whenever the ith domino falls, the I plus first also falls, and together these we can conclude that all dominoes fall. Yeah, please stop talking. Stop talking. Yes, please. Sorry, you raised hand long ago. Yes. Sorry, say it again, please. Say it again, please.
Isn't the implication the other way
This
around?
implication
Yeah.
or this?
That
Okay.
if the next term is true, then we imply that the first one was true.
No, we never. So here is the statement. The statement says, if the ith statement is true, if the kth statement is true, then the k plus first is true. if a statement is true, then the next one is also true. This is what we prove. If ith domino falls, then the next one also falls.
Meaning that if the next one is true, then
No, it doesn't mean that. It's a converse. You cannot just say, if I is true, then I plus 1 is true. If ith statement is true, then the I plus 1th proposition is true. It's not meaning, you cannot just say the converse. Okay, the converse is different. You can say equivalently that if pk plus 1 is false, then if not pk plus 1, then not pk. That's equivalent. The contrapositive is equivalent. Yes, please.
Can we say that this whole thing is a lot of direct proofs, like infinite direct proofs? Let's say that E implies usage. Can we say that this is a
Yes, that's a very good thing. So, not infinitely direct proof, that we don't do it like this, but these are infinitely many implications that we have to prove. If I want to use the proof, if I want to establish this thing, look at this, this is a direct proof method. If I want to do this, if this is true, then this is true, right? If this is true, then this is true. Now, I have to, if I want to prove that this is given, this is always true, okay? This is always true. This is like the, okay, I cannot prove to you the principle of mathematical induction. The principle of mathematical induction is an axiom. That's why I had to go through the voting, right? That if you are convinced that when I establish that the first domino falls, and that whenever the ith falls, then the I plus first will also fall, is it safe for us to assume, is it reasonable for us to conclude that all dominoes will fall? Many of you agreed, and the language of mathematics has agreed that okay, we will assume that this is a true statement. This whole thing is a true statement. It's assumed to be a true statement. It's the axiom. Okay, it's assumed to be true that in any world, if the first domino falls, and whenever the ith fall, then the I plus first falls. Right? This then is the if then. Okay, not the temporal then. That afterward. That if the ith fall, then the I plus first fall. Then we can conclude that all dominoes will fall. We assume this to be a self-evident true statement, okay, a meaningful, natural, reasonable statement. We assume that. Now, the way I'm going to go about it, I will prove that P of 0 is true, and I will prove these infinitely many implications. Of course, I cannot prove infinitely many implications one by one, so I'll have to prove it more generically, and so that's going to be the next section where we start actually applying induction for our purposes. Yes.
Does it only work in countable sets?
Very good question. Does it only work for countable sets? So, look at this. Right now, I've stated that this only works for countable set, not only just countable set. I've said it only works for the natural numbers. Generally, induction is used for the set of natural numbers. Okay, is used for the set of positive integers. That's what it is used for. We just established that if you take any other countable set, there is a one-to-one correspondence between natural number and that countable set. So, if you can kind of substitute that one-to-one correspondence, then you can use it for any countable sets. Okay, a statement about any countable set, you can use it. Okay, so let's just do an example. Hopefully, it will make things clear, and I want to do one counter example. This is a statement. We all know the truth of this statement. Okay, do we know the truth of this statement? Through many methods, okay, and we repeated it many times. The sum of the first I integers is equal to is n into n plus 1, or the sum of the first n positive integer is n into n plus 1 or 2. Can you make it a statement about all positive integers? Where is this all positive integers coming from? I am saying this is a statement about all positive integer.
N should be positive.
N is positive because I goes from 0 to n, so n is non-negative. But why this is a statement about one equality? I am saying this is not actually one equality, it is infinitely many equalities. what is written there? This number is equal to this number, right? That is inequality. It is not one equality in this statement. It will infinitely many equality. Where are those infinitely many equalities? For every n it gives me one equality. So, these are infinitely many equalities, right? For every possible value of n, which are infinitely many possibilities. So, that the ICP is asking you to state it as infinitely many statements, right? So, actually speaking, in the context, in the subtext, we were actually saying this statement, that for every natural number n, the sum of the first n positive integer is equal to n into n plus 1 over 2, right. So, this is actually the statement. The claim is basically this, right. We drop this for all n in, so this for all n was assumed to be there, right. It is like, what is it called, a subtext, or so there is a statement between the lines, right. Remember, I in the first lecture I told you, you should listen to what you should listen to what I mean, not listen to what I say. Okay. So, even though I did not say here for all n p of n, I meant for all n p of n, right. That is what you should have read. Okay. What is true? Can you stop talking, please? Yes.
If for all n belongs to n, the sum of I from 0 to n is equal to that, then for all n belongs to n, p of n is true. Like, shouldn't be an if.
No, no, no. This is true. There are infinitely many equalities, right? X is equal to y can be true or false. This is the only proposition here it is made. This is a different statement. This is not a logical OR, right? This is a shorthand way of saying exactly this thing. If you substitute p of n, then this statement is shorthand for p of n. We all are convinced about the truth of this statement, right? For any n, if I add the sum, the first n positive integers or the first n non-negative integers, I get n into n plus 1 over 2, right? The proof, induction proof works like this. I first write a statement, the proof is by induction on some variable k, right? Some variable n. So, this is important to see. This is called the induction variable, and when you have, once you have a multivariable statement, then it is important what are you inducting on, right. It will be, I will give you examples later. Then I have to establish those two facts, right. The first domino falls, and whenever the ith fall, the I plus first fall. The first domino falls, that statement is called the basis step, or the base case, right. So, I prove the base step, meaning I just explicitly prove that p of 0 is true when the value of k is 0 or 1 or 2, whatever is the first statement. The first of these infinitely many statements is true, right. These are infinitely many statements. The first statement is p of 0. P of 0 is true. I prove that, and next I prove that for all I, for all k, if p of k is true, then p of k is plus 1 is also true, right. And then I conclude that for all n p of n is true. So, what will be the base step? What will be the statement of the base state, the base case here, the basis step? What will we need to prove? What will we need to prove in the first step, in the basis step? The summation of I from 0 to 0. Yeah. The sum of I when I goes from 0 to 0 is equal to 0 into 0 plus 1 divided by 2, right. So, if you really state it, that is what whatever we said in English, this is the sum of I when I goes from 0 to 0 is equal to 0 into 0 plus 1 over 2, right. So, what is the sum of I when I goes from 0 to 0? Is just 0, right, 0 plus nothing or 0. What is this value? 0 into 0 plus 1 over 2 is 0, right. So, it says if I add 0 with nothing, I get 0, right, or if I add nothing, then I get 0, and that is a true statement. So, we establish, okay, yes, p of 0 is true. Out of all these infinitely many statements, the first one is true. Now, I am going to prove that if p of k is true, then p of k plus 1 is true, right. If p of k is true for any k, right, not for a fixed or a special type of k, for general k, right. If p of k is true, then p of k plus 1 is true, right. So, I apply a direct proof method, assume p of k is true. this assuming P of k is true is called the inductive hypothesis, right. And then using the inductive hypothesis, just the direct proof method, assume P is true, then Q is also true. This step from inductive hypothesis to the next statement P of k plus 1 is called the inductive step. Okay, that is just the syntax of this proof. So, I will assume that P of k is true. In other words, I will assume that the sum of I when I goes from 0 to k is equal to k into k plus 1 over 2. And then using the inductive hypothesis, I will prove P of k plus 1, meaning that the sum of I when I goes from 0 to k plus 1 is equal to k plus 1 times k plus 2 divided by 2. Okay. So, let us see, given the inductive hypothesis, if in a world where the first k numbers add up to k into k plus 1 over 2, is it also true that the first k plus 1 numbers add up to k plus 1 into k plus 2 over 2? Okay. So, suppose k plus I am going to prove this thing. This is equal to, by just simple syntactic manipulation of summation, the sum when I goes from the sum of I when I goes from 0 to k plus 1 is equal to the sum of I when I goes from 0 to k plus k plus 1, right. I just separated the last term out of this big summation, the red summation, I separated the last term. What is the blue term here? What is the blue term? The blue term, the blue term is the sum of the first k numbers, right. What can I replace it with? Why? It is not proven, it is assumed. We are applying the direct proof. We assume that P of k is true. If P of k is talking about this summation, so I can substitute this with k into k plus 1 over 2, right. By the inductive hypothesis, remember, if P then Q, assume P is true, I can use whenever I need this the statement P. Statement P is now given, right. Only in the world where P is true I am going to prove Q is true, right. So, I can assume, I have assumed the inductive hypothesis, I can use as much as I want, right. So, I use the inductive hypothesis and the rest is just algebra. Take k plus 1 common, you get k over 2 plus 1, which is actually k plus 1 over 2, okay, which is k plus 2 over 2. Okay. So, what I see, if this blue equality holds, then the red equality holds. Okay. This only if I cannot substitute if the blue statement, the blue replacement is not an option, I would not be able to conclude this whole equality. Okay. Let us do one more. Only if I cannot substitute if the blue statement, the blue replacement is not an option, I would not be able to conclude this whole equality. Okay. Let us do one more. The sum of the first n positive integer is n squared. We saw this also. Please settle down. Okay. I need to give you a few examples so you can think about it. I mean, I am not going to repeat this. The sum of the first n odd integer is n squared. Which course?